factorials and permutations. So what we're going to be learning about are different types of abbreviations for products in organized counting. Starting with factorial notation, many counting and probability calculations involve the product of a series of consecutive integers. You can use factorial notation to write such expressions more easily. For any natural number n factorial is equal to n times n minus 1 times n minus 2 times n minus 3 all the way down until 1. So we keep multiplying by consecutive numbers. And this is called n factorial. So for 4 factorial, that would be 4 times 3 times 2 times 1, always decreasing by 1 for each factor, and that's 24. Similarly, with 7 factorial, that would be 7 times 6 times 5 times 4 times 3 times 2 times 1. So on your calculator, try to evaluate 7 factorial. So you'll find this button, it might look like n factorial or x factorial, but try to evaluate that to go right to the step. We don't have to write this descending product. We can go right to our answer. So let's try to see one of those probability problems that we come across, or counting problem. How many ways can a band play a set list of 5 songs? By fundamental counting principle, we said that we have 5 choices for the first. Then, without repetition, we're not going to play the same song again, so there's 4 choices left, and then 3, then 2, then 1. Because there's one less option at each song. So therefore, this can be abbreviated as 5 factorial. And since we're going to be talking about rearranging items where we can't have repetition very often with organized counting, factorial notation is very helpful. So, that being said, this is specifically helpful for when we are rearranging all of the items. For example, this example has 5 songs. All 5 of the songs are being rearranged. Let's just investigate some of the values of factorials. Notice that it is growing very rapidly, and eventually your calculator might not be able to display this using the number of digits available in the window. So that being said, it's going to use exponential notation, where we talk about a power of 10. So we move the decimal over 10 places, and we have an approximate value for 14 factorial. And there's actually a number in which, or some point where a calculator will not be able to process a number that's so large. For example, Microsoft Excel tops out at approximately 70 factorial, but these are very, very large numbers which have very little context in many cases. So you can simplify calculations involving division of factorials by canceling. The expanded form of the expression will reveal which of the factors will cancel. For smaller numbers, you can use mental math. For example, 5 factorial and 3 factorial. If we were to write these in expanded form, which of the factors would be remaining? So if 3 factorial is 3 times 2 times 1, and this also contains that 3 times 2 times 1, we can cancel. This is in expanded form. Because 1 divided by 1 is 1, 2 divided by 2 is 1, 3 divided by 3 is 1, the only remaining factors are 5 times 4. So in some cases, this helps us do mental math quicker. For larger numbers, you can simplify to make calculation easier. 94 factorial divided by 90 factorial. If you press 94 factorial into your calculator, mine says error 2. The exact value of 94 factorial is approximately 1.09 times 10 to the 146. That's 146 digits to the right if we were to move this decimal. So it's too large for many calculators to process. So what we can do is use that knowledge of the expanded form and think what factors would be remaining. So you don't have to write this out every single time. This is for instructional purposes. But I want you to think of those factors from 90 and down canceling, and we're only left with those remaining values from the numerator. And therefore we can actually evaluate this even though we can't do it in parts by calculating the numerator and then the denominator. So our second abbreviation for multiplication of consecutive numbers is permutations. A permutation of n distinct items taken r at a time is an arrangement of r of the items in a definite order. So order matters. The total number of such permutations is denoted by NPR or PNR. Both are equivalent, just different forms that you might see. Both mean this exact same statement. N factorial divided by n minus r factorial, where n is the total number of items, and n minus r is the r is the number of items to be arranged. So we'll see how this works in context. Permutations are applied when the number of items being selected is less than the total number of items. So we have seen problems typically like this. How many ways can the letters of Greater Essex County District School Board be rearranged? There's 6 letters, so 6 choices for the first, 5 for the next, because we can't repeat the same digit, and because there's no repetition, we're going to have one less choice at each stage, and that's fundamental counting principle, but this can be abbreviated as 6 factorial. That's our first abbreviation. This is another way of writing this, which is seemingly more complex, but I want to show the connection between factorial and permutations. This is a permutation using 6 different numbers of length 6, because we're using each and every single one. Notice that this is just what the definition is. If you use your calculator, you can go right to 720. And this is an example just to stress that 6 factorial is 6 pick 6. You'll hear people often say, instead of permutations, 6 pick 6 of the items. All right, let's see, when does this apply? How many permutations can be made by selecting 3 letters of the word GECDSB? So we're only selecting 3. So if we're only selecting 3, we can still use fundamental counting principle. We have 6 choices for the first letter, 5 for the next, and 4 for the next, the third letter being chosen. That's 120. And instead of writing this calculation using fundamental counting principle, we could use 6 pick 3, because there are 6 items and we're only selecting 3 of them without repetition. Now, we don't have to show all these steps in between. Our calculator can take us right to this step from 6 pick 3 to 120. I'm just showing this step in between to show you that we are canceling in the denominator with the values in the numerator, so that you can maybe even look at some of these and do mental math. All right, so this is one case where we can see the advantage of permutations. 20 athletes are competing in a marathon. The leaderboard ranks the top 8 runners. How many different ways can the leaderboard be filled? So fundamental counting principle means that we think of the first place position. How many people could potentially be there? 20. The second place, 19. Third place, 18, and so on. But as you can see, as our selection size is pretty large, we have 8 athletes who will be on the leaderboard, the top 8, and we get this value. 5,079,110,400. In fact, with every configuration of the total number of athletes and the selection size, these numbers get very large very quickly. But in order to avoid a long string of multiplication, what we can do is use permutations. So this would be 20 pick 8. Notice that that 8 represents the number of positions that are being filled. And you can go straight from this step to your final answer. And you can see that that is less likely to have an error when entered into your calculator. Permutations with grouped items. To count the number of permutations where some elements are grouped side by side, use the following formula. N minus k plus 1 factorial times k factorial, where n is the total number of items, k is the number of grouped items, and we'll refer to these points with context in this example. The grouping method. 8 runners are competing in the 100-meter dash. If 2 runners are sisters, then how many ways can they be assigned to lanes which are side by side? So if they're side by side, what we can do is treat them as if they are one item. So we have 8 total runners. So we'll just call these people x1 through x6. Remember, subscripts are names in mathematics. But S subscript 1 and S subscript 2 are the sisters, and we're going to treat them like they're one item. So instead of having 8 total runners, we have 7 items that we're rearranging. And for each of those different permutations, we could switch these 2 items. They could have been placed anywhere in between, in any order. But if they're grouped together, S1, S2 could also be written as S2, S1. So the number of ways in which we can configure these two is 2 factorial, which is 2. And we listed which cases they are. Now, if we are interested in the number of ways that people are not side by side, that's difficult to calculate, so we have to use the indirect method. The indirect method includes taking all cases, and this spans all cases, the cases where they're side by side or they're not side by side. Using algebra, we'll isolate what we're looking for. We want the cases where they're not side by side, so subtract side by side from each side of the equation. Switching left and right hand side, we end up with all cases minus side by side will give us not side by side. So all cases, unrestricted, you can rearrange 8 runners in 8 factorial ways. If we are subtracting the cases where they are side by side, we just calculated that in the previous example, and the difference between the two gives us the number of ways in which they are not side by side. Lastly, to really challenge our understanding, we are looking for the in this case, 3 items being side by side. 12 books are arranged on a shelf. 3 of the books are written by Yuval Noah Harari. How many ways can the books be rearranged so that all 3 books by the author are side by side? So let's group these items. There's a lot. There's 12 total. But the last 3, we're going to say, are the books by this author. And let's think of if we were to group these items, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then this is all 1. So we'll call that 10 factorial. Now, for every single position in those rearrangements of these items with this selection here grouped, these items can be rearranged in 3 factorial ways. 3 factorial is 3 times 2 times 1, so I could rearrange this in 6 different ways every single time, no matter where it's positioned. So the product of these two will give us the total number of ways in which the 3 books can be side by side.